Welcome to the deep dive. Today, we're really jumping into something fascinating: how machine learning is changing hospitals, making them smarter, more efficient, better for patients, ultimately.
Yeah, and our main source here is some really interesting work by Homyra Oroujzadeh. It looks at AI, specifically in the digital shift in hospitals, focusing on the value it adds.
Exactly.
So our mission really is to explore how these algorithms actually help, helping doctors, hospital managers, not just theoretically, but getting, better diagnoses, treatments that work better, and handling resources much more effectively.
And what really gets me is how this isn't just about crunching numbers, it's like fundamentally changing how medical decisions get made, how patients are cared for. So, yeah, get ready because this is where it gets really interesting. We're going to get into the nuts.
Absolutely. And when we talk about these machine learning algorithms, they generally fall into, let's say, three main buckets: supervised learning, unsupervised learning, and reinforcement learning. And each one, as we'll see, has its own specific, really valuable uses inside a hospital. They tackle different kinds of challenges with data.
Okay, let's unpack that then. Starting with supervised learning. Now, these work with labeled data, right? So every piece of data kind of comes with an answer already attached.
That's right. Like maybe historical data on how long a patient took to recover, or an image that's already marked as benign or malignant. That label is what trains the algorithm.
Got it. And the source mentions linear regression as a key one here. So how does that help in a hospital?
Well, linear regression is really good for predicting continuous things, trends. So imagine you feed it patient data, maybe age, blood pressure, how much heart damage they have.
Mm.
It can then give a pretty good estimate of how long it might take that patient to get stable after,
Yeah.
say, heart surgery.
Okay. So it's estimating recovery time and the practical benefit of that.
Well, it massively helps with planning the post-op care,
Yeah.
managing bed turnover more efficiently, staffing nurses,
Yeah.
and, even giving families a clearer timeline, which can reduce a lot of stress during a really tough time. It smooths out the logistics.
Okay, that makes a lot of sense. Gives doctors a clearer roadmap and the hospital better control over resources. What about complex images, though, like MRIs or CT scans? Is there a go-to algorithm for that?
Yeah, for image analysis, the support vector machine, or SVM, is really powerful.
VM.
It's great at spotting complex patterns in those kinds of images. A classic example is telling the difference between a benign tumor and a malignant one.
How does it actually do that? What's the mechanism?
So SVM tries to find the best possible line or boundary, technically a hyperplane in multiple dimensions that separates the data points.
Uh-huh.
So points representing healthy cells on one side, maybe cancerous cells on the other. Finding the optimal separation, the one with the biggest margin, makes the classification really robust, even if the data is a bit messy. This helps radiologists be more confident in their decisions, reduces maybe some ambiguity, and can potentially speed things up, which is crucial in areas like oncology.
It's basically finding the best dividing line.
Got it.
Got it.
Okay, so that covers labeled data pretty well. But what happens when you've just got heaps of raw data, no labels, and you need to find patterns you don't even know are there? That sounds like unsupervised learning territory.
Exactly. With unsupervised learning, there are no predefined answers. The goal is discovery, finding hidden structures or patterns in large data sets.
Right.
And a good example from the source is principal component analysis, PCA. It's what we call a dimension reduction algorithm.
Emission reduction.
Okay, that sounds technical. If you've got super complex medical data, what does reducing dimensions actually do for you?
Think about something like genetic data. You might have thousands of features, thousands of markers for just one person. It's overwhelming.
Yeah, absolutely.
PCA helps boil that down.
Yeah.
It finds the main patterns, the principal components, that capture most of the important variation in the data, but with far fewer dimensions.
Ah, I see.
So it makes the data easier to work with, less noisy perhaps, and helps you focus on the most significant patterns, maybe combinations of genes linked to a disease like cancer, much faster. It cuts through the complexity.
Okay, that makes sense. Finding the important signals in all that noise. What about k-means clustering? That was another one mentioned. How's that used?
K-means is all about grouping. It takes your data points, maybe patients, and puts them into categories based on how similar they are according to their health data.
So, like patient groups.
Exactly. Take diabetic patients, for instance. K-means could analyze their lab results, symptoms, maybe even genetic info, and group them.
Hmm.
These groups might line up with known types like type 1 or type 2 diabetes, but, and this is really cool, It might also uncover new subgroups,
Oh, interesting.
patients who share certain characteristics that mean they might respond better to a very specific personalized treatment plan that wasn't obvious before.
Wow, okay. So it helps tailor treatments much more precisely. Very useful. Right. That brings us to the third category, reinforcement learning. This sounds different again, more about making decisions.
That's absolutely right. Reinforcement learning is about learning through interaction. Think of it like teaching a system through trial and error. Gets rewards for good decisions, penalties for bad ones.
Okay.
Cue learning is a common example. And in a hospital, it's particularly useful for optimizing dynamic problems like resource management.
Right, resource management. Can you give a specific example, maybe where the old ways struggle?
Sure, a great one is managing hospital beds in real time. It's a constant juggling act.
I can imagine.
Traditional methods might use fixed rules or rely on someone manually trying to figure it out, which can easily lead to bottlenecks,
Okay.
or beds sitting empty when they're needed. With Q learning, the system is constantly deciding which available bed is best for this incoming patient. It considers the patient's condition, what's happening on different wards, maybe even predictions about who else might arrive soon.
So it's learning constantly.
Exactly. If assigning a patient to a specific bed quickly leads to good outcomes, like shorter wait times and efficient use of that ward, the system gets a reward.
Hmm.
If it causes delays or inefficiency, it gets a penalty.
Uh-huh.
Over time, after thousands of these decisions and feedback loops, it learns the optimal strategy for allocating beds to keep things flowing smoothly, minimizing waits, maximizing usage.
That sounds incredibly efficient, like having a super smart, tireless manager just focused on bed allocation 24/7.
Pretty much, yeah. It adapts to the real-time situation.
Okay, so let's just quickly recap then. Based on this dive into Homyra Oroujzadeh's work, it's really clear machine learning is playing a huge role in making hospitals smart. We've seen it predicting recovery times, helping diagnose tumors from images, finding hidden patient groups, and even managing resources like beds intelligently. It's really embedded now.
And that value-added perspective is key. These aren't just fancy tech tools. They actually allow hospitals to use their data way more effectively,
Right.
which leads directly to, more accurate diagnoses, better patient management, treatments that are better optimized.
Hmm.
It all adds up to genuinely improving patient outcomes. It makes a real difference.
That was a fantastic overview, really insightful. Thanks for breaking that down. Now, as we always do, we want to leave you, our listener, with something to think about. A final, provocative question.
Hmm.
Given just how powerful these algorithms are analyzing data, helping with critical medical decisions, what do you think is the single most crucial thing we need to consider, or maybe the biggest challenge we face, in rolling these out widely and making sure they're used completely safely in healthcare? Something for you to mull over.